Hyperbola. Parabola. Ellipse. Circle. Do you know how they originate? And how important they are in planetary motions? In this 3D animated tutorial, you will learn all these answers and concepts. Hyperbola, parabola, ellipse, circle, etc. are based on a same concept, but with slightly different parametric values. To define any one of them, you need to consider three basic things. Number 1. A fixed straight line, which is called directrix in this context. Number 2. A fixed point. It is called focal point and is named as S. Number 3. A moving point. It is named as P. Now, if P moves in such a manner that, at each and every position, the ratio of the distance from the point P to the focus S, that is SP, and distance from the directrix, that is PM, remains fixed, and also greater than 1. Then, the trajectory of the point P is called a hyperbola. The ratio, SP, by PM, is termed as the eccentricity of the conic. For hyperbola, values of eccentricity lies between 1 and infinity. If the point P moves through a closer path to the directrix, then the curve becomes flatter, and eventually becoming a straight line as it touches the directrix. In this special occasion, eccentricity reaches an infinite value. Since SP is 0 in this case. Isn't interesting? Thus, straight line is also a conic, and its eccentricity is infinity. An infinite eccentricity can be achieved if the point P moves through the directrix. If the point P moves through a closer path to focus, the trajectory tends to become a parabola. We will discuss parabola later in this tutorial. Actually, hyperbola, by default generated in pair. This second curve is called a conjugate hyperbola, and is a mirror symmetrical to the first curve. Also, note that there exists a secondary directrix and a secondary focal point. The closest distance between these two curves is known as semi-major axis. These two closest points are vertex points, and a perpendicular bisector of the semi-major axis is called a semi-minor axis. The point where these axes intersect is the center of the hyperbola. In Cartesian coordinate system, general equation for this curve looks something like this. Here, h, k, is position of the center of the hyperbola. The numerators, a, and b, are the lengths of the semi-major and semi-minor axis, respectively. Now, allow point P to move in another style. This time, it keeps the ratio, SP, by PM, fixed, and equals to 1. This trajectory is a parabola. Thus, parabola is a conic, whose eccentricity is exactly 1. In Cartesian coordinate system, the equation for this parabola may be like this 1. Here, h, k, is the coordinate of the vertex, and a is the distance between the focus and the vertex, and also, vertex to the directrix. Again, let us move the point P with a new constraint. This time it moves in such a way that the ratio of SP and PM remains fixed and less than 1. In this way, the trajectory it creates is called an ellipse. Unlike hyperbola and parabola, an ellipse is a closed curve. By symmetry, it also has two directrix and two focal points and two vertex points. A straight line segment, connecting both vertex points, is called a major axis. This is the longest diameter of an ellipse. Similarly, the shortest diameter of the ellipse is known as the minor axis. The general equation for an ellipse is written like this. Here, h, k, is the position coordinate of the center of the ellipse. It is the point where major and minor axis cross each other. 2a and 2b are the lengths of the major and minor axis respectively. Note that eccentricity of an ellipse lies between 0 and 1. Check that, nearer the directrix, lesser circular the curve is. Now, move the directrix away from the focus. You can easily note that the length of the PM is increasing. Hence, eccentricity should be decreasing. And the elliptic curve is becoming more and more circular. Eventually, when the directrix reaches infinity, it becomes a circle. And then, its eccentricity goes to 0. The two focal points superpose each other to become its center. Major axis and minor axis becoming equal in lengths and convert itself into the diameter of the circle. Thus, circle is a conic whose eccentricity is 0. General equation for a circle is like that. Here, h, k, is the position of its center. And r is the radius. Before going to describe importance and application of conics in planetary motions, let us summarize. A straight line is conic, with infinite eccentricity. A hyperbola is also a conic. But its eccentricity lies between infinity and unity. If eccentricity is exactly 1, then it is a parabola. Ellipse is a conic whose eccentricity lies between 1 and 0. And finally, eccentricity of a circle is simply 0. Almost all objects found in the space or in motion, they usually follow straight paths if no force acting on them. But in our solar system, all planets are under direct control of our sun. Hence, orbit of each of them are more or less elliptical. Their eccentricities lies between 0.007 to 0.246. The orbit of Pluto is highly elliptic, while Venus revolves through an orbit which is almost circular in shape. In general, planetary orbits are elliptical, with two focal points. The Sun resides at one of its focal points. Distance from the Sun is not constant during a complete revolution. The position at the shortest distance is called perihelion. Similarly, the position of the farthest point is known as aphelion. Those comets, whose orbits are elliptic, can return our solar system after a period of time. Like Halley's Comet. It reappears in every 76 years. Will be visible again in mid-2061. Tempel 1 is another such comet, which will visit the Sun on March 4, 2022. But orbits of many comets, or asteroids, are either hyperbolic or parabolic in nature. Hence, these objects never return to our solar system. Oumuamua is one such asteroid, which comes closer to the Sun on September 9, 2017. And will never return to the solar system. Another such asteroid is C2021A9. First detected by Pan-STARRS in 2021. It is likely to visit the solar system in year 2023. Hope you enjoyed the topic and learned easily.